Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics. This lecture is entitled Additional VHDL Topics, Top-Level Designs, and Variables. There's a grab bag of VHDL topics that do not necessarily fall in neither combinational nor sequential, and so we're going to go ahead and discuss some of these topics in very general terms. However, these are things that you probably have already seen in labs. What I'm trying to do is go ahead and refresh some of those things in labs, give you a formalized lecture on them, and we'll be making use of some of these additional VHDL topics as we discuss sequential devices a little bit later. First and foremost is this difference between a variable and a signal. Thus far, all we've been discussing is signals, and I know sometimes I slip up. I know I say variable, but when I mean in VHDL, what I mean a signal is something that is concurrent, whereas a variable is something different. Process. We've talked about if statements and case statements. When is a signal assigned? The answer is it's assigned at the end of the process statement. So as you go through that process statement, you may be performing expressions, evaluating inputs on that sensitivity list. However, those expressions are not evaluated, nor are the signals assigned until the end of it. A variable is something different, okay? A variable inside a process, it is updated throughout that process. And I know this may not mean anything to you now, but there's something a little bit later we'll introduce. It's called a for loop, and it will do something a specific number of times. And let's say that thing, that expression that you're trying to evaluate inside that for loop, it's usable data. It wouldn't make sense if it was updated only at the end. You want to make use of that. So that's how you use a variable. We'll go into it, how they're applied in for loops. But I'm going to do a very simple example about variables. And just think of this little expression that I've drawn right here. I've got A and B inputs, and I've got X outputs. All I'm doing is I'm taking the standard logic vector A, which consists of elements A1 and A0, and standard logic vector element B1 and B0, and I'm ORing the respective standard logic bit positions to form another output, X, which also is a standard logic vector. This simple example here also illustrates the incredible power of the standard logic vector. Because what is the expression for this thing? It's really is X is a signal that is assigned A or B. I don't have to put in those designations A0 or B0 is assigned signal X0 is assigned that, nor do I have to write X1 is assigned A1 or B1. The standard logic vector takes care of that expression. What if I wanted, though, in addition to the output X, I wanted the complement of X? And the answer is put a NOT gate on there. Okay, and one would think that this would work, but it doesn't. The reason why it doesn't, it's pretty simple. X, I've assigned it's a standard logic vector 1 down to 0. It's an output. Can I generate complement X, which is also an output, from an output? The answer is no. VHDL does not allow you to write the expression complement X signal is assigned not X, because it's this. If X here has been defined as an output, you can't generate outputs off an output. One of the simplest ways to potentially do that is define that standard logic vector X not as an output, but as an in-out. Okay, so there's 3 different directions. There's in, out, and an in-out. That is one way of solving that problem. There's another way of solving that problem. You could potentially do something like this, where complement X is the knotted expression of A or B. But these two things look very similar. They look very similar. But notice here, this one at the top here, I am generating output off an output, and this one below, I'm generating output from inputs, and I am generating output from inputs. Okay, and I can write that as A nor B. Okay, that's complement X. So that's a way of doing it. So we've solved that potentially by doing a in-out direction for X. We've also solved it by generating the knotted expression of an input for that. There's another way of doing that, and that's the making use of a variable. If a variable is updated inside a process, what I can do is use a process statement to kind of do this right here. And I know I said I couldn't do it with a signal, but I can do it with a variable. And how I would do that is I would use this process. So let's go ahead and I'm going to write something out here. So here's an architecture statement, and again, that architecture statement here, it's starting with our architecture, our begin, we're indenting everything inside there, and then we're ending it up right there. So everything inside here is inside those begin and end. So let's go ahead and get rid of that, and what I'm going to do is just talk about this process statement right now. So if we remember it, a process statement has a sensitivity list. Potentially I could put a name for it there. If I've got a bunch of these running at the same time, I might want to differentiate them. Very similar to an architecture statement, there is a declaration section for a process statement. And how I'm going to do that, I'm going to, again, stylistically, I don't care how you do it, this is how I'm going to do it. I'm going to indent in my declaration section. What am I going to declare? Well, I'm going to make use of a variable. And that's what I'm kind of drawing up here at the top. This is really what I want to create. I want to create a temporary variable. And that's what you can think about a variable is. It's a temporary signal, okay? It's not really a signal though. It's a temporary one. And I'm going to generate V0 and V1, and then at the end of the process statement, I'm going to go ahead and do that. Okay, so what am I going to do in a declaration? I've got to declare a variable. Okay, so that's how you actually declare a variable. What do you call it? Variable. It's a keyword, it's a reserved word. You can't call a variable because it's reserved. This is almost like those internal signals that we've generated previously. So I'm just declaring it. Now how do I do that? A signal, if you remember right, X is assigned, X signal is assigned A or B. That's a signal declaration. If I do V, which is a variable, all I do is I change that to a colon. Okay, so that is the one difference between a signal assignment versus a vector assignment. So now I'm going to go ahead and just inside that process statement, I'm going to begin it, and what am I going to do? I'm going to say variable V is assigned my expression. And now what I can do is I can actually, at the end of the process statement, this is when these guys get evaluated. X and complement X. What is X? Well, it's V. What is complement X? Now I can write that not V, because V is not really an output, it's a variable. And again, what am I doing is I'm making use of the fact that they're all standard logic vectors. V0 is assigned to X0, V1 is assigned to X1, and so on and so forth for complement X, and V's for the not V's. And then what do you do? End the process statement, at which point signal X is assigned V, complement X is assigned not V. Okay, that might have seemed a little unnecessary for a variable, but it illustrates its pretty key topics. Variables become pretty increasingly important as we do use them in things that have a very sequential nature, like for example a for loop, which we'll be discussing later. The top level design. Okay, we've introduced this in labs before, and you may have seen this in some of the supporting lecture material. A top level design is a good idea, and it's always a good idea to wear a hat when it's cold or whatever. Do you have to do a top level design? The answer is no, but you might, if you wore a hat, feel a little bit more comfortable. Okay, a top level design is that it's making use of the structural approach where we instantiate components. And what it is, its purpose is to do is to provide a single top level VHDL program that is device specific. And what I've done here is, in the background, I've got the IC Project Navigator going, and I'm going to go ahead and show you how I've used a top-level design for this exact expression that I've written here. But what I'm doing is I'm creating a VHDL program that does this process here. And then what I'm going to do is I'm going to go ahead and use it as a component, a single component in the top-level design. And that's exactly what a top-level design is. You take this thing with inputs A and B and output X and complement X. It's a reusable program that is not device specific. And if I wanted to program it on a Nexus 2 500 or a Nexus 2 1200, or in this case a Nexus 3. So a Nexus 3 has a Spartan 6 FPGA on it. Okay, and it would be obviously understandable that the pin assignments for a Spartan 3E versus a Spartan 6, they could be different. So what I'm going to do is I'm going to use a top level design to to instantiate this single VHDL program and then call it in that top level. The top level, however, what I'm doing, what are my inputs and outputs? It's the device-specific inputs and outputs. In this case, it's switches and LEDs. Okay, so let's go over and switch over to the IC Project Navigator and illustrate what I'm talking about. Okay, so here we are in the window of that VHDL program that is illustrating exactly what I went over there, and no difference so far. Where I'm at is here, and notice that it is a component of top level, and the UCF file, the user constraints file, is also a component of top level. So there I am at, this is the description, what is it? Here is my entity. Notice I'm using very general terms, A, B, X, and complement X. I'm not using device specific pins. Architecture, within that architecture, here's I'm beginning it, and then I'm ending my architecture. Inside that architecture, I have got a name for that process. In this case, I'm calling it variable demo, the statement process, and its sensitivity list. I've got to go ahead and do my declaration for variable v. It's a standard logic vector. In this case, it's got two elements, 1 and 0. I'm going to do the expression, the variable assignment. V is assigned A or B. And again, we're making use of the fact that A is a standard logic vector. It's taken A0, ORing it with B0, creating V0. And then what I'm going to do, now I can do my signal assignment. When does the signal assignment occur? As soon as I end the process. So far, nothing different. But what I'm purposely doing here is I'm purposely using a different device than I have previously in any of these other example problems. If I went into the user constraint files for some of the examples I've used before, a Nexus 2 1200, and went in and changed the name for LED to X0, X1, comp X1. It's kind of a pain. So what I can do is kind of use the general UCF file. Okay, and what I've got here is, in this case, is the Nexus 3 UCF file. Wouldn't it be handy? This is a huge file. Wouldn't it be handy if I just use the name in this particular example here, LED 0 for an output? Notice that they're not using parentheses on that. So different syntax between a UCF file and VHDL. What if I use these as names and I could just port map a component to those specific inputs and outputs? So let's go back to here, the IC Project Navigator, and that's exactly what a top level does. I just go to my top level, and it's the exact same thing. My entity, what is my entity? Well, in this particular case, I've got switch inputs, 3 down to 0, and I've got 4 LED outputs. What are the two inputs? A has 2 inputs, B has 2 inputs, so there are my 4 inputs. What are my 4 outputs? Well, it's 4 LEDs, because I've got to generate X0 and X1 and complement X0, complement X1. So there are my 4 outputs. So I've got the entity statement for that device specific. Now all I do for my architecture, start my architecture, end my architecture, and declare a component within it. What is the component I'm going to use? Well, the one I just generated. It's the exact same port, A, B, and X, and complement X. So there's my ins. Those are my general statement. They're not device specific. Whereas switches and LEDs, those might be device specific. And what I'm going to do is now port map it. I'm going to instantiate that single component and port map it up to the device that I want. In this particular example, I'm using the user constraints file for the Nexus 3, and I've added it as a source to this project, and I can go ahead and now check my syntax, do the place and route, and program this device based off these pin configurations. Now, what's the major advantage of this? What is the advantage of instantiating a single component in this top level description? Well, the answer is if I want to use a Nexus 2, all I got to do is just make sure the pins and LEDs have those same numbers, just import the UCF file for the Nexus 2. If I want to potentially have buttons as the input instead of switches, go to that top level. Rather than call it switch, put in BTN. So it's a nice way of potentially easing a transition between device and device. The pure core of this thing, how this thing behaves, it's still going to behave just like we talked about in our variable demonstration. It's going to still generate X is equal to A or B. However, via those top level designs and those user constraint files specific to the device, I can potentially ease the transition from device to device. This concludes this portion about additional VHDL topics, variables, and top level designs. Let's go on into some new data types and some new operators.